Okay class, I have your next assignment here. Now remember class, your project is due on the 26th. If you haven't started your assignment yet, I'm not looking forward to yours. I guess I better get started. Well, I guess I've got some analyzing to do.
A few moments later.
Oh, I fell asleep. Oh, I'm screwed. I missed the whole movie. Oh. What?
Hey kid, wake up! Oh. You ready to do some physics, kid?
Who are you?
Who am I? Vin Diesel, of course.
Why is Vin Diesel teaching me about physics? I was just in a car with you, we just drove off a building.
In case you hadn't noticed, you're in a dream right now. You're stressing over that project you have to do tomorrow, so I'm here to help you out. Let's get this done.
So, you want to know if this stunt is possible? Well, we can use some projectile motion physics to figure this one out. First, let's find some values. A Lamborghini Lykan Hypersport is 4.5 meters long, according to Wikipedia. There are about 4.5 Lambos between the two buildings, so 4.5 times 4.5 is 20.25 meters. After hours of research, here's what I've done to find our vertical distance. The towers jumped in this scene are the Atwood towers. The arrangement of these towers is as follows. Now after some rewatching of the scene, it appears we jump from Tower 2 to Tower 3. Tower 2's top floor is 281.6 meters high. There are 74 floors, so 281.6 divided by 74 is 3.8 meters per floor. Looking back on the scene, it appears we dropped 3 floors in total. So 3.8 times 3 is 11.4 meters. This gives us our... Now we solve for our time using this formula on the left. This will get us our time of 1.53 seconds. Then we use our horizontal distance over our change in time to get our initial velocity in the horizontal. This gets us 13 meters per second. Now, we need to find how much distance the Lamborghini needs to accelerate to 9.9 meters per second squared. I got this value from Wikipedia, 62 miles per hour in 2.8 seconds. We use this formula here to find out our distance. We need 8.8 meters in total. Is there enough room? Assuming the building is in a circular shape, what's the diameter of the building? According to Wikipedia, Tower 2's area in total is 83,738 meters squared. Now per floor, we take that number and divide by 74 to get the area per floor, which is 1,132. We then use this equation to find the diameter of the building. This equation will get us 37.9 meters. So if they started from halfway, they'd still have enough room to reach this speed. They would still have 18.95 meters. This jump should be possible, but this is ignoring the different coefficient of friction between the tires and the marble floor.
Wow, that actually really helps. But I have a question. Why did you have to bring me in the scene with you?
I brought you inside the scene so you could visually see what was truly happening and understand it better.
So what now?
Now, we move on to scene 2. It's okay. I do something really sick while you just sit by and watch. So enjoy.
Oh, come on.
What's she doing?
atmosphere.
Oh, can we please stop teleporting? Like, I'm feeling sick.
How cool was that?
Yeah, that definitely looked awesome, but I don't think it's possible.
What? No way. How is that not possible?
Well, first, let's start with our equations here. We're going to be working with momentum. So, momentum is mass times velocity, and the momentum before the crash is equal to momentum after the crash. Now, I've got this equation here used for the momentum before or after the crash, which is the mass and the velocity of the first object and the mass and velocity of the second object. Now, I've rearranged that equation to kind of fit what we're working with here, with the car and Vin Diesel and all that stuff. Now, I rearranged this one to find the final velocity of Vin Diesel. So the way this is rearranged is the final velocity of the car is equal to 0 because it crashed into the barrier, so that means all momentum is transferred into Vin Diesel himself. So, after moving some stuff around, we take this piece here and then we try and get the final velocity of Vin Diesel, so we set it equal to that, divided by his mass, and we should be good to go. I have some values here from the mass of Vin Diesel, 102 kg, the mass of the car, and the velocity of the car, assuming that he was going about 60 miles per hour. It's 26.8 meters per second. And these are the websites I got all those values from. So after we substitute those values, we get a velocity of Vin of 415 meters a second, which is a little bit wild, considering that in the scene that was definitely not what was happening. Then we take the same equation, but we substitute some different values for the girl, her name's Letty, so she's flying through the air, and I took her mass, the mass of the tank, and the speed of the tank, and so I got her mass from healthyceleb.com. Then this tank is called a Chieftain Battle Tank, and its mass is 55 long tons, or 55,883 kilograms, which is massive. And I got its speed because it's been modified for the movie to go 60 miles per hour. And so, after substituting those values, her final velocity would be 27,507 meters per second, which is a little bit crazy. So looking at the diagram here, this is not to scale, by the way, because her vector here, her velocity vector, which should be way longer, and his could probably be like that big, but just so that you can see what's properly going on, it's a bit bigger. And I assumed an angle of 30 degrees of what she's getting launched off of and what he's getting launched at, like 45 degrees, just by looking at the scene. And yeah, now we get to do some vector math. So now we have to do our vector math. We are going to assume that Vin Diesel is V1 and Letty is V2. So for V1 we need to find the X and Y components. Because it's a 45-degree angle, they're both 293.5 meters per second. However, the X component is negative because he's traveling in an opposite direction that she's traveling in. And then we look at her X and Y components and we get these big numbers. They're just, I don't feel like saying them. And then to find the resultant velocity, we add and subtract like the X component and the Y component of the two. And we get these values here, which then we put into like a Pythagorean theorem equation here. We add the square root of each number together, then square root, and we get a resultant velocity of 27,619 meters a second, because they do stick together on impact. So they don't collide off each other, they stick and keep traveling, and this is how fast they'd be traveling. Which seems a little bit unreasonable, considering the fact that they kind of floated across this gap and then just happened to land on the windshield of a car and, you know, crack the window but not go ripping through it. But we're going to look at the consequences of that now. So one of the first consequences is that they're traveling at 61 degrees north of east. So if you look at the diagram here, that's just this this angle here, so just in this line. And in the scene, they collided and they continued to travel that way. But according to the diagram, he would not push her any further because she has such a large momentum because of the mass of the tank and the speed that she would just rip right through him. So it doesn't really make any sense, and there is a gap between the bridge and the scene. I'm not sure if you noticed that they leaped over. They would probably go either into that gap or onto the other side of the road. And again, traveling at such high speeds, there's no way they'd survive. Alright, so number 2, I was looking at the acceleration of Vin Diesel, because if he's traveling at 60 miles per hour and suddenly all the car's momentum gets transferred into him and he launches up to 415 meters a second, I was wondering what's the acceleration. And we get 3,882 meters a second squared, which is really high, and humans are capable of surviving really high speeds, but acceleration that fast is what kills us. So that's the problem in this situation, is how fast they accelerate. And same with Letty, the girl he's trying to save. It's just way too fast. I put it over 0.1 seconds because it was almost instantaneous that he was launched off the car and she was launched off the tank. So I mean, I thought that made sense. And obviously they're not constantly traveling at accelerating at the speed, because you know there's air resistance and stuff because they're flying through the air so fast. But it's hard to make this scene possible because of how fast they're traveling at, and just the changes in momentum is pretty crazy. So I don't know how this scene could be possible in any way whatsoever. So I think that this is probably the most unreasonable scene in the Fast and Furious movies ever. So Vin Diesel, that is why it's not possible. It's just, I proved it to you. So now what?
Okay, kid, you proved me wrong. But I've got another scene for you now.
Great. Do I at least have to do something this time?
Oh yeah, definitely.
This one better be possible.
Let's hop in and see. So what'd you think of that? Is this one not possible either?
Okay, here's why it's not possible. So, we're going to get some values first. We have the Dodge Charger SRT-8, which is the two cars used in the scene. The mass, 1,890 kilograms, and then we found the acceleration here. I took the speed over time that I found from this website, and I got the acceleration and the coefficient of friction between the roads and the tires. Now for the high security vault, we know that the vault itself is 10,000 kilograms because it was stated in the movie. The coefficient of friction between the vault and the ground when it's static, so when it's not being pulled, is 0.7. Like before they start moving the vault. But once the vault's moving, the coefficient of friction is lower, it's 0.45. They just have to get it out of its state of just sitting there. And then the money inside the safe, there's $100 million inside. And in the movie it was stated it was 49 kilograms per pack of money. And so 49 times 100 is 4,900 kilograms of money inside the safe. So the total mass of the safe is 14,900 kilograms. And then got this diagram here. So now we need to figure out our net force that the cars are pulling, and we need to figure out the force of friction that's being that's restricting the cars from pulling the safe. Alright, so we're going to calculate some stuff. To get the net force of the cars pulling, take the mass times acceleration. So I took the mass times 2, because there's 2 cars, and times 7.5, which gets us 28,350 newtons, which is quite a bit. And this is also, I noticed they're hooked up to the safe like this. I thought at first there was like they were connected to the same point, which I'd have to do some vector math, but I'm not. I'm just going to treat it as one because they're both kind of going straight. And so now we look at the force of friction. So I took the static force of friction, multiplied by normal force, which is just gravity times the mass, and then got a force of friction of 102,000 newtons, which is pretty incredible. So yeah, to find the total force, they still have to overcome 73,864 newtons of friction force pulling. So the fact that they spin out in the scene and then all of a sudden just get some grip and just pull it out of the wall makes absolutely no sense, because they wouldn't even make it start moving. Okay, so another way to look at this problem too is we know that the force friction of the vault has to equal the force friction of the tires so that the cars can be moving. And so we take the static coefficient of friction of the vault times the mass of the vault, and that'll get us this big number here. And then we take the coefficient of friction of the tires times the mass of the car, and then times the weight distribution, because I thought it makes more sense to calculate that value in, and then times 2 because there's 2 cars. Now, calculating this out, we are still really far behind, which means it doesn't make sense. And even with generous friction, if I said there was a coefficient of friction of 1, still doesn't work. Still, if we ignore the weight distribution, good coefficient of friction is still 1800 times 2, which is still not good enough to overcome. So now we're going to make it possible. And to do that, we would have to increase the force that the cars are pulling. And so we'd have to increase the number of cars if we're not changing them, because different cars have different accelerations and can pull more. But if we stick with this car, we have to increase the number of them. And using this equation that I made, we get 7.2. So to overcome it, we'd need 8 cars in total just to get the safe moving. It's still stuck in the bank. And now with the kinetic friction, so with the safe moving now, we need, it gets to 4.6, so we need 5 cars, which is a little bit like, how would you do that? And so now we check if the friction matches. So this is because of weight distribution. So when the safe is static, stuck, like not moving in the bank, we get this equation, except a times by 46 divided by 54, because that's the weight distribution of the car. And so we get 9.25, which means we need 10 cars, so even more. And then for kinetic friction, same thing, it's just times 0.45, because that's the coefficient of friction of the safe when it's moving. And we get 6 cars in total, which I don't think you'd have enough room on the road for that, too many cables tangling up and stuff, so I do not think this is possible. And yeah, where to now?
Our final scene's coming up soon. Don't worry, you're not in this one. Are you ready to prove me wrong again?
Stretch him out! Hold him!
Get out of there.
I'm working on it.
Stop working on it and do it.
No! It's my business!
Okay, you have to admit it. That one was pretty awesome.
Okay, Vin, let's work out this problem together. So I made a diagram here. It's a force vector diagram, and it's not to scale because obviously we have 20,000 newtons here and 7,000 here, and they're kind of the same length. It's just because it would make things smaller, it's easier to see that way, so just note that this is not to scale. And then I found all the models of the cars and the forces they're pulling because I found the acceleration. So I believe I'll put a website here and it'll say where I got the models and the accelerations. And so I put the, let's say 60 miles per hour in 5.6 seconds. So I put it like that, and then I got these values for the accelerations, and then you multiply by the mass of the car, and then we'll get the net force that they're pulling on Vin Diesel's car in the middle here. And then there was an overhead view of the scene where I kind of looked and kind of assumed what the degrees of the forces were and which direction they were pulling in. And then I set I set the north end to positive and the east end to positive, and then opposite negative, because we're pulling in different directions. And then we get to do more vector math. So I didn't show all of my calculations because that would just take up the whole whiteboard. So I showed the first one on this car, and so like the x and y component. So I just took the hypotenuse times sine 30 to find the x component, got that, and then same thing for y except with cos. Kind of makes sense, and I did that for all these cars, and then I found all the forces they were pulling back. And then, yeah, so the x component for this car, for example, would be negative because it's pulling towards the negative quadrant for how I set this up anyways. And so some values are negative, some are positive. So when we add them all up and throw them together, we get negative 9,230 newtons for the x component, and then negative 12,794 for the y component. And so it should be going this direction, and so I made a little diagram just to show what it kind of looks like. It's not to scale again. And then our resultant would be 15,776 newtons, which is quite a bit. And so we take that, and then that would be our net force, and then we take all the mass of the cars, and we put the force over the mass, and we get our acceleration of around 1.1 meters a second squared. So they wouldn't be moving very far, they'd just kind of be like accelerating this way a little bit, which kind of makes sense because the forces aren't going to be constant, they're going to be kind of pulling, and so I think that makes sense, which is a good thing. And then yeah, we got 54 degrees south of west, so this direction here. And I also calculated the mass and the acceleration of Vin Diesel's car here, and the net force came out at 7,901 newtons. So we're going to need that for our next little problem we're looking at here. Okay, so in the scene we notice that Vin Diesel's car, which is car 6 in my diagram, pulls car 4, which means he has to overcome the y components of these 3 vehicles. So I took the y components of those 3 vehicles, added them together to get my net force for the fourth car, which is all 3 of those. And then for him, I took the y components of this one, and his total force, just because he's going straight back, put it as my net force, my net force number 6. And so I made this equation that if we take F net 6 and then subtract F net 4 from it, it has to be greater than 0 or else he won't be able to pull the car. And after putting those values in, turns out he would not get pulled at all, or he would not pull the car at all. And he does apply some nitrous oxide as he's doing it, but it still isn't enough. It doesn't add like hardly any force to him. So, and especially when he applies it, it's not, he's going backwards and he applies it so that he can go forward, which doesn't make any sense. So that is also a problem. But now we're going to look at, after he does pull, how, if it's possible for him to flip Roman's car completely over like that. So we're going to look at that now. Okay, so deciding whether or not he can flip Roman's car, we're going to do a torque problem. And so we're going to act like the front tire is a pivot point so that it flips over like that. And so I drew a little diagram here. Force of gravity is pulling the only thing keeping the car from tipping over. And then we have the tension force of the cable attached to Vin Diesel's car that's going to flip him over. And so to make this easier, I just pretended like this is going straight forward and it's hooked up to the top of the car, so the tension force is going straight. And then this is about a 60-degree angle here, which means that this one would be 60 degrees as well. And then we get this equation, force of gravity cos theta has to be less than force of tension sine theta. So basically, force of tension sine theta has to be greater because needs to overcome gravity in order to flip it. And so the force of tension is just all the Y components pulling back on the car that we kind of looked at in the last problem there. And then we take this calculation, we go through with it, and then we get these values here. So 26,000 is bigger than 11,000, so it would be easy for him to flip the car just because there's so much force pulling him over. And so, does this seem possible, not possible, or more reasonable than the last two? I think it's definitely more reasonable than the last two, but there were some things that we looked at that weren't quite possible, like the pulling the car back in the first place. But I think the flipping is definitely possible. So yeah, we're all done now, aren't we?
Yeah, kid, I think we're done. I don't think I could say goodbye. I'm gonna go take a sad drive.
And when brotherhood come first, then the line will never be crossed. Established it on our own when that line had to be drawn, and that line is what we reach. So remember me when I'm gone.
Without you, my friend, and I'll tell you all about it when I see you again.
Thought you could leave without saying goodbye?
I used to say I lived my life a quarter mile at a time. And I think that's why we were brothers. Because you did too.
Started out small to a real bond. Cause we're brothers first. Cause we're been through a lot, but it ain't over. We gon' keep it.
You'll always be with me.
Change the game without even knowing.
And you'll always be my brother.
How can we not talk about family when family's all that we got? Everything I would do, you were standing there by my side. And now you gon' be there for the last ride. How can we not talk about family when family's all that we got? Everything I would do, you were standing there by my side. And now you gon' be with me for the last ride. And now you gon' be there for the last ride. Let me tell you. Yeah, we came a long way. I'll see you again.
Oh, that whole thing was a dream? Oh, at least I know how to do my project now.